Hello there, and welcome to Sleepy Science Vault. There is a question so vast, so quietly astonishing, that most of us have never fully sat with it. Not just how the universe began, but whether the word before even makes sense when you ask it. Tonight, we are going to explore that question together. Slowly. Without rushing toward answers that may not exist yet. We tend to imagine the Big Bang the way we imagine a firework, a single brilliant point, erupting outward into darkness. But that picture, as vivid as it is not quite right. The Big Bang did not happen in one place. It happened everywhere at once. Every point in space was part of it. There was no center. There was no edge. There was simply an entire universe, blazing into existence all at the same moment. What the Big Bang actually describes is not an explosion into empty space. It describes space itself, along with everything inside it, expanding outward from an extraordinarily hot, extraordinarily dense early state. The universe was not born inside something larger. It was the something larger, from the very first instant. And in those earliest moments, even light could not move freely. The universe was so hot, so dense, so overwhelmingly energetic that matter and radiation were locked together in a single, churning, opaque state. There was no sky to look up at. There were no stars. There was not even a clear path for a photon to travel. The early universe was, in a sense, completely hidden from itself. This is one of the strangest realities of cosmology. We live in a universe that holds its own origins just out of reach. We can look back billions of years. We can detect the faint glow of ancient light that has been traveling toward us since the universe first became transparent. But beyond a certain point, the view goes dark. Not because nothing was there, but because the physics of that era made observation impossible, even in principle. The Big Bang model is remarkably good at explaining what happened after those first moments. The formation of hydrogen and helium. The gradual cooling of space. The slow gathering of matter into clouds, and clouds into galaxies, and galaxies into the vast cosmic web we can map today. In all of this, the model works beautifully. But it goes quiet when you ask about the beginning itself. It does not fully explain the initial conditions. Why was the universe the way it was in that first instant? Why those temperatures, that density, those particular laws of physics? The model describes the evolution of the universe with extraordinary precision, while the starting point remains, for now, an open question. And then there's perhaps the deepest puzzle of all. Physicists cannot directly observe anything that might have existed before the start of time and space. Not because our telescopes are too small, or our computers too slow. But because the very framework we use to ask scientific questions, cause and effect, before and after, here and there, may have had no meaning before the universe existed. One leading idea among physicists is that time itself began at the Big Bang. If that is true, then asking what came before it is a little like asking what is north of the North Pole. The question sounds meaningful. But the geography simply does not allow for an answer. There is no before to point to, because time was not yet a thing that existed. And yet, human curiosity being what it is, physicists have not simply accepted that and moved on. They have looked for other ways in. And one of the most compelling ideas to emerge in recent decades is something called cosmic inflation. Inflation proposes that in the tiniest sliver of time after the universe began, fractions of a second so small they have no name in ordinary language, space underwent a period of expansion so rapid it makes the word fast feel completely inadequate. The universe did not just grow. It stretched exponentially in almost no time at all. This idea was not invented to sound dramatic. It was proposed to solve real puzzles. Because when we look at the universe today, it is almost perfectly flat, geometrically speaking. And it is almost perfectly uniform, with the same temperature and the same density in every direction, even in regions that should never have had time to communicate with each other. Inflation explains both of these things elegantly. It says the universe was once small enough that those regions were connected, and then inflation stretched it all outward before the hot, dense Big Bang phase fully took hold. In this picture, inflation happened first. The hot Big Bang came after. The two are not the same event, even though we often speak of them together. But here, too, the questions deepen rather than resolve. Scientists still do not know what powered inflation. They have proposed a kind of field, sometimes called the inflaton field, that may have driven this expansion. But it has never been directly detected. And NASA, reviewing the current state of our knowledge, puts it plainly: researchers still do not know what caused inflation, or what, if anything, existed before it began. So we are left, at the very edge of everything we know, standing before a horizon we cannot yet cross. The universe is real. The laws governing it are real. Our ability to understand them, layer by layer, century by century, is one of the most remarkable things about being human. And still, the first moment waits. Quiet. Patient. Just beyond our reach. We have already seen that the Big Bang was not an explosion in space, but the beginning of space itself. We have seen how inflation may have stretched the infant universe faster than any speed we can imagine, and how time itself may have simply not existed before that first moment. These are not small ideas. They are some of the most quietly staggering conclusions in all of human thought. But knowing what we do not know is, in its own way, a form of knowledge. And when it comes to the era before or during the very first moments of creation, what we do not know is enormous. Some physicists have proposed that in those earliest moments, energy was not something that existed inside the universe, carried by particles or fields moving through space. Instead, energy may have been woven into the fabric of space-time itself. Space was not an empty stage on which energy performed. Space and energy were, in some deep sense, the same thing. The geometry of the universe and the forces shaping it may have been inseparable, part of one unified, blazing whole. It is a difficult idea to hold in the mind. We are used to thinking of space as a container, and of energy as something that fills it. But the early universe may not have respected that distinction. The container and its contents may have been one. This possibility points towards something physicists have been reaching for across decades of work: a theory that unifies the very large and the very small, a framework that can describe the universe not just after it cooled and settled, but in the very instant of its creation. That framework does not yet exist in its final form, and the search for it is one of the great ongoing adventures of modern science. The theories that try to describe the pre-Big Bang era, quantum gravity, string theory, loop quantum cosmology, and others, are serious scientific frameworks. They are built by careful, rigorous thinkers using some of the most sophisticated mathematics ever developed. But they share one honest limitation: none of them have been confirmed by direct observation. They are our best attempts to reason beyond the edge of what we can see. But they remain, for now, educated speculation. String theory, for instance, proposes that the most fundamental units of reality are not particles but tiny, vibrating strings of energy, whose different modes of vibration produce the different particles and forces we observe. In some versions of string theory, the universe we live in is just one of many possible configurations, one solution among an almost incomprehensibly large landscape of possible universes, each with its own physical laws. String theory is studied in part because it offers a potential path toward unifying quantum mechanics and general relativity, two frameworks that are both extraordinarily well tested, but which, when applied to the same situation simultaneously, produce contradictions. At normal scales, those contradictions do not matter much. But at the very beginning of the universe, they matter enormously. And standard physics, as currently understood, simply cannot navigate that territory. The specific problem has a name. It is called quantum gravity. And it sits at the heart of nearly every open question about the universe's origin. Gravity, as Einstein described it, is the curvature of space-time. Mass and energy bend space, and that bending is what we experience as gravitational attraction. This picture works beautifully at the scale of planets, stars, and galaxies. It even works at the scale of the entire observable universe. But quantum mechanics, which governs the behavior of the very small, describes a world that is fundamentally probabilistic, where particles do not have definite positions or states until they are measured, where energy comes in discrete packets, and where uncertainty is not a limitation of our instruments but a feature of reality itself. These two frameworks, general relativity and quantum mechanics, have never been fully reconciled. And at the Planck scale, the regime of the very early universe where distances are unimaginably small and energies are unimaginably large, both frameworks are needed simultaneously. Gravity is no longer negligible at the quantum level. Quantum effects are no longer negligible at the gravitational level. And without a complete theory of quantum gravity, we simply cannot say with confidence what was happening. The Planck epoch is the name given to this earliest stage of the universe's existence. It lasted from the very moment of the Big Bang to approximately 10 to the power of -43 seconds afterward. A duration so brief it has almost no meaning in ordinary human terms. And yet, everything that followed, every star, every planet, every ocean, every moment of consciousness that has ever existed, traces its origins back to what happened in that incomprehensibly small window of time. Current physics cannot describe it. Not because physicists are not clever enough, though the problem is genuinely hard. but because the theoretical tools we have were not built for those conditions. They work beautifully outside that window. Inside it, they give answers that stop making sense. Infinities appear where there should be finite values. The equations break down. This breakdown has a specific name as well. It is called the Big Bang singularity. General relativity, when traced backward in time, predicts that all the matter and energy of the universe converges to a single point of infinite density and infinite temperature. A singularity. But most physicists believe that singularity is not a real physical object. It is a sign that the theory has been pushed beyond the limits of its own validity. It is the map running out of road. Whatever was actually happening at that moment almost certainly does not involve true infinities, but describing it accurately requires a theory we do not yet have. And so scientists do something they are very good at. They look for clues wherever they can find them. One of the most important sources of those clues is something called the cosmic microwave background. It is, in a sense, the oldest light in the universe, radiation that was released when the universe had cooled just enough for atoms to form and light to travel freely for the first time. That moment happened roughly 380,000 years after the Big Bang. Ancient by human standards, but extraordinarily early in cosmic time. The cosmic microwave background fills the entire sky. It reaches us from every direction, a faint, nearly uniform glow of microwave radiation, just a few degrees above absolute zero. And embedded within it, in the form of tiny fluctuations in temperature from one region of the sky to another, is information. The patterns in that ancient light carry the imprint of conditions that existed in the very early universe, before stars, before galaxies, before any of the structure we see today had formed. Cosmologists study those patterns with extraordinary precision. The shape of the fluctuations, the way they are distributed, the specific scales on which they appear, all of these carry information about inflation, about the density of the early universe, about the relative amounts of ordinary matter, and dark energy. Every mission that has mapped the cosmic microwave background with greater resolution has returned with new layers of insight, and also new questions. But even the cosmic microwave background has limits as a window into the past. It can only show us the universe as it was after it became transparent. The earlier, opaque era is hidden behind it, inaccessible to light-based observation. To see further back, we need a different messenger. Gravitational waves may be that messenger. Gravitational waves are ripples in the fabric of space-time, produced when massive objects accelerate, when neutron stars spiral together, when black holes merge, when the early universe itself underwent rapid changes in its energy distribution. Unlike light, gravitational waves do not interact strongly with matter. They pass through everything almost unimpeded. In principle, gravitational waves produced in the primordial universe, in the first moments after the Big Bang, or even during inflation, could still be traveling through space today, carrying information from an era that no telescope will ever directly see. Detecting those primordial gravitational waves would be one of the most extraordinary scientific achievements in human history. It would give us a way to probe physics at energies and timescales that are completely inaccessible by any other means. It would be, in a very real sense, hearing the sound of creation. The technology to detect these faint, ancient ripples is still being developed. Current gravitational wave detectors, like LIGO and Virgo, have made breathtaking discoveries, confirming the existence of gravitational waves, detecting the mergers of black holes and neutron stars across enormous cosmic distances. But primordial gravitational waves are far subtler, far quieter. Future instruments, both on the ground and in space, are being designed with this goal in mind. And so the search continues. Across the cosmic microwave background. Across the spectrum of gravitational waves. Across the deep theoretical territories of string theory and quantum gravity and loop quantum cosmology, where mathematicians and physicists work in a realm that has not yet been touched by direct experiment. It is humbling, in the best possible way. We live on a small planet, orbiting an ordinary star, in one of hundreds of billions of galaxies. And yet we have looked up, and asked, and measured, and reasoned our way back almost to the very beginning of time. We have built instruments of extraordinary delicacy. We have developed theories of almost incomprehensible sophistication. And we have arrived, honestly and openly, at the edge of what we currently know. Beyond that edge, the questions do not disappear. They simply wait. Patient as the universe itself. Science, at its best, is not a collection of answers. It is a living conversation between what we observe and what we think we understand. And in cosmology, the study of the universe as a whole, that conversation is more active, more unresolved, and more genuinely exciting than it has been in decades. We have already explored the Big Bang, and the strange silence that surrounds its earliest moments. We have seen how cosmic inflation was proposed to explain the flatness and uniformity of the universe, and how gravitational waves and the cosmic microwave background serve as our deepest available windows into that ancient era. But a window is only useful if you know how to read what you see through it. And reading the early universe correctly requires theories that can be tested, compared, and if necessary, discarded. This is one of the most important and sometimes underappreciated aspects of modern cosmology. Even the most elegant theory about the origin of the universe is only scientifically meaningful if it makes predictions that match what we actually observe. The cosmic microwave background, with its precise temperature fluctuations across the sky, is one of the most demanding tests any origin theory must pass. The large-scale structure of the universe, the way galaxies cluster into filaments and walls and vast empty voids, is another. A theory that cannot reproduce these observed patterns, no matter how mathematically beautiful it may be, does not describe the universe we live in. And so new models of cosmic origin are increasingly judged not just by their internal consistency, but by whether they make predictions that can actually be checked. Whether they say something specific about what the cosmic microwave background should look like, or how matter should be distributed across cosmic scales, or what the spectrum of primordial gravitational waves should reveal. This shift toward testability has raised the standards of the field considerably, and it has forced some theories that once seemed promising to be reconsidered. Inflation itself, the very framework that has dominated early universe cosmology for decades, is not immune to this scrutiny. inflation has been remarkably successful. It explains the flatness of the universe. It explains why the cosmic microwave background looks almost identical in every direction, even in regions that should have been causally disconnected. It explains the origin of the small density fluctuations that eventually grew into galaxies and galaxy clusters. In all of these ways, it has passed observational tests that were not even imagined when it was first proposed. And yet, inflation has unresolved difficulties that its supporters acknowledge openly. The most fundamental of these is that we still do not know what caused it. NASA, surveying the current state of the field, puts it plainly: scientists do not know what powered cosmic inflation, or whether anything came before it. The proposed mechanism, a field called the inflaton, which briefly dominated the energy content of the universe and then decayed into the hot plasma of the Big Bang, remains hypothetical. No direct evidence for the inflaton field has ever been detected. It is inferred from the outcomes it is supposed to have produced, which is a reasonable scientific approach, but not the same as direct confirmation. There is also a deeper philosophical tension within inflationary theory. In many versions of the model, inflation, once started, never completely stops. Different regions of the inflating space exit inflation at different times, producing an enormous number of separate universes, each potentially with its own physical laws and constants. This idea, known as eternal inflation, raises questions that are genuinely uncomfortable for science. If the theory predicts essentially anything is possible somewhere in this vast multiverse, does it actually predict anything specific about our universe? A theory that can accommodate every possible outcome is, in a certain sense, very difficult to falsify. And the ability to be falsified, to be wrong in principle, is one of the cornerstones of scientific methodology. These tensions have encouraged physicists and cosmologists to explore alternatives, or at least complements, to the standard inflationary picture. One such alternative begins not with inflation, but with a particular kind of space called de Sitter space. In de Sitter space, the geometry of spacetime is shaped by a positive vacuum energy that belongs to space itself, independent of any matter or radiation present. Our universe today, driven by what we call dark energy, appears to be approaching something like a de Sitter state. And some theorists have proposed that the universe may have begun in a similar configuration, a de Sitter-like state in which the fabric of spacetime was already infused with this kind of vacuum energy, setting the stage for everything that followed. The appeal of starting from de Sitter space is partly mathematical. It has a relatively clean and well-understood structure. It allows theorists to apply tools from quantum field theory and curved spacetime with greater confidence than they can in more extreme environments. Whether it accurately describes the actual beginning of the universe is another question entirely, but it offers a controlled setting in which to explore ideas that would otherwise be intractable. More broadly, a growing number of models have moved away from the idea that the Big Bang was the absolute beginning of everything. Instead, they propose that the Big Bang was an event, a dramatic transition, that emerged from a pre-existing state of some kind. In these frameworks, there was something before. Something that, through its own dynamics, eventually gave rise to the hot, expanding universe we inhabit. what that pre-existing state might have been varies considerably from model to model. In some versions, the universe existed in a stable or nearly stable configuration, not expanding, not collapsing, but persisting in a kind of equilibrium, before some perturbation or quantum event triggered the transition into rapid expansion. The Big Bang, in this picture, is less a creation and more a transformation. The universe did not come from nothing. It came from something that was, in some sense, already there. This idea recurs in several different theoretical traditions. In loop quantum cosmology, for instance, the Big Bang is replaced by what is called the Big Bounce. The universe did not begin at a singularity. Instead, a previous contracting phase reached an extreme density at which quantum gravitational effects halted the collapse and reversed it into expansion. Our universe is, in this model, the rebound of a universe that came before. In string gas cosmology and certain other string theory-inspired models, the universe may have spent an extended period in a high-temperature, nearly static configuration before the dynamics of string theory drove it into the expanding phase we now observe. These models make specific predictions about the nature of primordial fluctuations, predictions that differ in subtle but potentially measurable ways from those of standard inflation. And this is where the question of testability becomes critically important. Because if some of these models predict different patterns in the cosmic microwave background, or a different spectrum of primordial gravitational waves, then they are not just philosophical alternatives. They are competing scientific hypotheses, and future observations may have the power to distinguish between them. Some of the newer models go even further in challenging the role of inflation. A small but serious group of researchers has explored whether cosmic inflation is actually necessary at all, or whether alternative mechanisms might explain the features of the universe that inflation was invented to address. Some of these models attempt to explain the origin of the large-scale structure of the universe, the distribution of matter that eventually became galaxies and galaxy clusters, without invoking an inflaton field. Instead of a scalar field dominating the energy content of the early universe and driving exponential expansion, these approaches look to other physical mechanisms, other ways in which the seeds of structure might have been planted. Among the most intriguing of these proposals is the idea that gravitational waves themselves, ripples in spacetime produced in the very earliest moments, could have played a role in seeding the formation of galaxies. In standard cosmology, the seeds of structure are quantum fluctuations that inflation stretch to cosmic scales. But in some alternative models, it is the gravitational wave background of the primordial universe that imprints the initial perturbations from which structure grows. This is a bold proposal. Gravitational waves interact very weakly with matter. In ordinary circumstances, they pass through everything without effect. But in the extreme conditions of the early universe, at energies and densities that dwarf anything in the current cosmos, their influence could have been far more significant. If this mechanism can be made to work quantitatively, and if it produces a pattern of structure that matches what we observe, it would represent a genuine scientific revolution, a complete rethinking of how the universe acquired the shape it has today. It is worth pausing to appreciate the scale of what is being attempted here. Cosmologists are not simply asking how galaxies formed, or how stars ignited, or how planets assembled from dust and rock. They are asking how the conditions for all of that arose, how the universe came to have the right properties, in the right amounts, distributed in just the right way, to allow everything we see to eventually exist. And they are asking whether a completely different early history might have produced the same result. These questions sit at the very edge of what science can currently address. Some of them may be resolved within the coming decades, as next-generation telescopes, gravitational wave detectors, and cosmic microwave background experiments come online with greater sensitivity. Others may require theoretical breakthroughs that no one has yet imagined. And some may remain, for a very long time, genuinely open. There is something comforting in that openness, if you allow yourself to feel it. The universe is not a solved puzzle. It is a living question. And the people devoting their lives to exploring it are not chasing certainties, they are following the oldest human instinct there is. The need to look outward, to wonder, and to ask what lies beyond the last horizon we can see. The answers, when they come, will not diminish the mystery. They never do. They simply reveal a deeper layer waiting underneath. There is a particular kind of satisfaction that comes from discovering that something complicated may have a simpler explanation than you thought. Not a cheap simplicity, not the kind that glosses over difficulty, but the deep, elegant simplicity that sometimes emerges when a theory is finally built on the right foundations. In the study of the early universe, that kind of elegance has been hard to come by. The standard picture has required additions and amendments, inflation added to explain flatness and uniformity, the inflaton field added to drive inflation, dark energy added to explain the current acceleration of expansion. Each addition is scientifically motivated. Each solves real problems. But the accumulation of separate components, each requiring its own explanation, leaves many physicists with a quiet dissatisfaction. A sense that the full picture has not yet come into focus. And so, alongside the work being done to refine and test inflation, a parallel effort has been underway for years, an effort to see whether the features we attribute to inflation might emerge naturally from physics we already know, or from deeper frameworks that do not require a separate inflaton field at all. Some models have made genuine progress in this direction. Rather than invoking a new scalar field with specially tuned properties, these approaches look to the structure of spacetime itself, or to the behavior of known fields in extreme conditions, to generate the early expansion and the patterns of structure we observe. The appeal is conceptual as much as mathematical. If early expansion can emerge from the underlying geometry of the universe, rather than from a field that has never been directly detected, the theory becomes leaner, more constrained, and in many ways more falsifiable. One of the most striking recent developments along these lines comes from a framework called quadratic quantum gravity. In 2026, a quantum gravity model built on this foundation made a specific and testable claim about the early universe, that the rapid early expansion we associate with inflation is not the result of a separate field driving it from outside, but rather emerges naturally and inevitably from the deeper structure of spacetime at very high energies. In this picture, the expansion is not something imposed on the universe. It is something the universe does on its own, as a consequence of how quantum gravity behaves when energies are extreme enough. What makes quadratic quantum gravity particularly interesting from a theoretical standpoint is a property called UV completion. UV, in this context, refers to ultraviolet, to very high energies and very short distances, the regime where standard physics tends to break down. Many theories of quantum gravity struggle at these scales. When you push them to their limits, they produce infinities, inconsistencies, results that cannot be physically interpreted. A UV-complete theory does not have this problem. It remains mathematically stable and well-defined even at the most extreme energies imaginable, including those of the very early universe. This stability is not a minor technical detail. It is what allows the theory to say something meaningful about the Planck epoch and the moments surrounding it, the very era that has been inaccessible to other frameworks. But what gives this model its scientific teeth, what lifts it from an interesting theoretical proposal into something that can actually be engaged with empirically, is a specific prediction it makes about primordial gravitational waves. The model predicts a minimum detectable level of primordial gravitational waves. Not an approximate range, not a vague suggestion, but a floor, a lower bound below which, if the theory is correct, the signal cannot fall. This is exactly the kind of prediction that separates a scientific theory from a philosophical one. It says, if you look carefully enough, you will find at least this much. And if you look and find nothing, then something in the theory needs to be reconsidered. Future gravitational wave experiments, both ground-based and space-based, are being designed with precisely this kind of sensitivity in mind. If primordial gravitational waves are eventually detected, and if their amplitude matches the range predicted by quadratic quantum gravity, it will represent a profound validation, not just of one model, but of the entire approach of seeking early universe physics in the deep structure of spacetime rather than in ad hoc additional fields. We are not there yet. The experiments are still being built. The theoretical work is still being refined and debated. But the fact that a quantum gravity model can now make a prediction specific enough to be tested by instruments that will actually exist, that is genuinely new. That is progress of a kind that would not have seemed possible even a decade ago. And yet, for all the forward momentum of these new approaches, there is another set of ideas that has been developing along a quieter, deeper track. Ideas that do not simply ask what drove the early expansion, but question whether the Big Bang itself, the singular, unreachable beginning that classical physics describes, was really a beginning at all. The Big Bounce. It is one of the most ancient intuitions in human thinking about the cosmos, the sense that the universe might be cyclic. That what we call the beginning was really a turning point. That before our universe expanded, something else contracted. That the cosmos does not begin and end, but breathes. In modern physics, this intuition has found a rigorous expression in loop quantum gravity, one of the leading candidate theories for reconciling quantum mechanics with general relativity. Loop quantum gravity describes space not as a smooth, continuous fabric, but as a network of discrete, quantized units, a kind of fine-grained weave at scales far smaller than anything we can currently probe. Space, in this framework, is not infinitely divisible. It has a minimum size. A quantum of area. a quantum of volume. This discreteness has a profound consequence when you trace the universe backward in time. In classical general relativity, that backward journey leads inevitably to a singularity, a point of infinite density where the laws of physics cease to apply. But in loop quantum gravity, that journey encounters something different. As the universe contracts and its density approaches the Planck scale, the quantum nature of space generates an effective repulsive force, a pressure that resists further compression. And at some critical density, extreme beyond anything in our ordinary experience, but finite, not infinite, the collapse halts and reverses. The universe bounces. What we call the Big Bang, in this picture, is not the origin of everything. It is the moment of maximum compression and a transition between a contracting phase and an expanding one. Before our universe was expanding, there was a universe contracting. And before that, perhaps, another expansion. And so on, stretching back through a sequence of cycles that may have no beginning in the conventional sense. This is a deeply different picture from the one most of us carry. We are accustomed to thinking of the Big Bang as the absolute start, the moment before which there was nothing. Loop quantum cosmology does not require a nothing. It requires a before, populated by a prior universe following its own arc through cosmic time. The mathematics of loop quantum cosmology is sophisticated, and the details of what happens at and around the bounce are still being actively worked out. But several features of the model are already well developed. The singularity, that point where classical physics breaks down entirely, is replaced by the bounce. The equations remain valid throughout. There is no moment where the theory throws up its hands and produces meaningless infinities. The physics continues, across the bounce, in a way that can in principle be traced. This continuity is more than an aesthetic preference. It means that, in principle, the state of the universe before the bounce could influence the state of the universe after it. Properties of the pre-bounce universe, its geometry, its content, the fluctuations present in its final moments, might leave imprints on our universe that we could, with the right observations, detect. The cosmic microwave background, once again, becomes a source of potential clues. So do the statistics of primordial gravitational waves. If the universe bounced, the signature of that bounce might be encoded in the oldest signals we can observe. The search for those signatures is underway, though it is painstaking work. The expected effects are subtle. Distinguishing a bounce signature from the effects of standard inflation, or from primordial gravitational waves generated by other means, requires a level of observational precision that we are only beginning to approach. But the conceptual implications are staggering, and worth sitting with quietly for a moment. If the big bounce is real, then our universe is not the first. It is an episode in a longer story, a story that may have been unfolding for far longer than any time we can currently measure or imagine. The light we see, the matter we are made of, the very laws governing our existence may be the inheritance of a cosmos that came before, compressed into an almost incomprehensible density, and then released again into a new expansion. We would be, in a very deep sense, children of a previous universe. There is something profoundly strange about that idea. And something, if you let yourself feel it, profoundly beautiful. The universe not as a single, solitary story with a beginning and an end, but as something that renews itself, that carries its own history forward through the most extreme conditions imaginable, and emerges on the other side still coherent, still lawful, still capable of producing stars and planets and eventually minds that wonder about all of this. Whether this is how things actually work, we do not yet know. The honest answer, the scientific answer, is that loop quantum cosmology is a serious framework being seriously explored by serious people, but it has not been confirmed by observation. It makes predictions, and those predictions are being compared to data, but the verdict is not yet in. What we can say with confidence is that the question of what came before the Big Bang is no longer purely philosophical. It has become, in a genuine and growing sense, a scientific question. One that different theoretical frameworks answer in different ways. One that future experiments may have the power to illuminate. And one that, for now, remains beautifully, compellingly open. The universe keeps its deepest secrets carefully, but it leaves clues everywhere for those patient enough to look. Somewhere in the architecture of modern physics, there is a quiet revolution taking place. It does not make headlines the way particle accelerators do, or the way telescope images of distant galaxies capture public imagination. It happens in the language of differential equations and quantum operators, in seminar rooms and research papers exchanged between a relatively small community of people who have dedicated their careers to one of the hardest problems in all of science. But what they are working toward is nothing less than a complete reimagining of what the beginning of the universe actually was. We have already seen how loop quantum gravity replaces the smooth, continuous fabric of spacetime with something discrete, a fine-grained structure at the smallest possible scales, where space itself comes in irreducible minimum units. And we have seen how this discreteness leads naturally to the big bounce, replacing the classical singularity with a moment of maximum compression followed by a new expansion. But the story of loop quantum cosmology goes considerably deeper than that broad outline suggests. The details, when you look at them carefully, reveal a picture of the early universe that is stranger, richer, and in many ways more satisfying than the classical account. One of the technical achievements of loop quantum cosmology that deserves more attention than it typically receives is the way the theory handles time. In classical physics, and even in most quantum theories, time is a fixed background, a river that flows steadily while events unfold within it. But in general relativity, time is not fixed. It is part of the geometry of space-time, and it curves and stretches along with space in response to matter and energy. When you try to build a quantum theory of gravity, this creates a deep problem. The equations that govern quantum evolution normally require a fixed time parameter to make sense. But in a fully relativistic theory, there is no such fixed parameter. Time itself becomes a dynamical variable, subject to quantum uncertainty. Loop quantum cosmology addresses this through the use of what are sometimes called internal clocks. Rather than measuring the evolution of the universe against an external, fixed time, the theory tracks the universe's state relative to some physical quantity within the universe itself, a matter field, or the volume of space, which changes in a monotonic way and can serve as a proxy for time. The universe, in other words, measures its own evolution. It does not need an outside reference. And crucially, this internal clock keeps ticking through the bounce. The equations remain well-defined and continuous across the moment of maximum compression. There is no gap, no singularity, no point where the theory breaks down and leaves a blank. What this means physically is profound. The evolution of the universe through the bounce is not chaotic or indeterminate. It is, within the framework of loop quantum cosmology, deterministic. Given the quantum state of the universe just before the bounce, the theory in principle predicts the quantum state just after. The Big Bang is not a wall beyond which we cannot see. It is a doorway, extreme, yes, almost incomprehensibly so, but a doorway nonetheless, through which the state of the prior universe passes and re-emerges transformed. This deterministic evolution is one of the features that makes loop quantum cosmology scientifically attractive. It is not simply asserting that something existed before the Big Bang without being able to say anything about it. It is providing a framework in which that prior existence has consequences, in which what came before can, in principle, influence what came after in calculable ways. That is a meaningful scientific claim, not just a philosophical one. Several detailed models within this framework have been developed over the past 2 decades, and they share a number of common features that are worth examining. One is the behavior of the universe's volume near the bounce. In classical general relativity, as you trace the universe's history backward, its volume shrinks toward zero, toward the singularity where density becomes infinite and the theory breaks down. In loop quantum cosmology, this does not happen. The quantum geometry of space prevents the volume from reaching zero. There is a minimum volume, extremely small, but finite and non-zero, below which the universe simply cannot be compressed. Space resists annihilation at the quantum level. This minimum volume is not arbitrary. It is set by the fundamental scale of loop quantum gravity, the Planck scale, where the quantum nature of spacetime becomes dominant. And its existence is what generates the effective repulsive force that causes the bounce. As the contracting universe approaches this minimum volume, the quantum pressure builds. The contraction slows. And at the moment of minimum volume, the direction of cosmic evolution reverses. Expansion begins. The quantum effects that produce this behavior do not just prevent the singularity. They replace it with a smooth, continuous transition. The singularity is not merely softened or smeared out. It is removed entirely. The pathology that classical physics produces at the beginning, the breakdown, the infinities, the loss of predictability, does not appear in the quantum theory. In its place is a bounce, fully described by continuous mathematics, connecting a prior contracting phase to our current expanding one. Models developed within this framework explicitly show the universe undergoing a contracting phase before the expansion we observe. This prior contraction need not have been identical to our current expansion running in reverse. The quantum corrections that become significant near the bounce can alter the dynamics in ways that break the simple time reversal symmetry you might naively expect. The universe before the bounce and the universe after the bounce may have been quite different in character, different in their rates of change, different in the distribution of fluctuations, potentially different even in some of their large-scale properties. And here is where the story opens into genuinely new territory. Because some of the models developed within loop quantum cosmology and related frameworks make a striking additional suggestion that the Big Bang may not have been triggered by the collapse of an entire previous universe, but by something rather more local. Something we observe happening in our own universe today. The collapse of black holes. A black hole forms when a massive enough object collapses under its own gravity to such an extreme density that not even light can escape from within a certain radius, the event horizon. Inside that horizon, in classical general relativity, the collapse continues without limit, producing a singularity at the center. A point of infinite density, hidden from the outside universe, where the laws of physics again break down. But in loop quantum gravity, just as the cosmological singularity is replaced by a bounce, the singularity inside a black hole may be replaced by a bounce of its own. The collapsing matter reaches the Planck density, quantum gravity effects become dominant, and instead of continuing to collapse into a singularity, the matter rebounds. It expands. And in some models, this expansion does not occur back into the black hole's parent universe. It occurs into a new region of space-time, a new universe, connected to ours only through the deep interior of the black hole, but otherwise separate. Expanding on its own. Potentially developing its own stars, its own galaxies, its own complex structures over time. This idea, sometimes called the black hole universe hypothesis, or black hole cosmogenesis, is associated most prominently with the physicist Lee Smolin, though it has been developed and explored by others as well. The core proposition is that our universe may itself have originated from the interior of a black hole in a parent universe. The Big Bang that began our existence was not a creation from nothing, but the rebound of matter that had collapsed to Planck density inside a black hole, crossed the quantum bounce, and began expanding into what we now call our universe. If this sounds speculative, it is, and its proponents acknowledge that openly. But it is not empty speculation. The framework makes predictions. One of them concerns the geometry of the universe on the largest scales. In the standard picture, the universe appears to be spatially flat, or very close to it. But some models of black hole cosmogenesis predict a slight positive spatial curvature, a universe that is very gently curved, like the surface of an immense sphere, rather than perfectly flat. The deviation from flatness would be tiny, well within the margins of current observational uncertainty. But future measurements, made with sufficient precision, could in principle detect it. A confirmed detection of positive curvature would not prove black hole cosmogenesis, but it would be consistent with it, and inconsistent with certain other models. It would be a piece of evidence, a narrowing of possibilities. There is another prediction these models make that connects back to something we explored earlier. In some versions of the bounce cosmology, whether the bounce involves an entire prior universe or the interior of a black hole, the early acceleration of the universe that we normally attribute to inflation is not driven by an external inflatant field. Instead, it emerges directly from the bounce dynamics themselves. The quantum repulsive force that causes the bounce does not simply halt the contraction and reverse it cleanly. It produces an overshoot, a burst of expansion that has some of the same characteristics as inflation, arising naturally from the quantum geometry of the bounce rather than from any additional ingredient. This is a genuinely elegant possibility. If the early acceleration of the universe can be traced not to a hypothetical field whose properties must be carefully specified, but to the intrinsic dynamics of quantum gravity at extreme densities, then the theory becomes leaner and more powerful simultaneously. It explains more with fewer assumptions. And the predictions it makes about the spectrum of fluctuations in the cosmic microwave background, and about primordial gravitational waves, may differ in subtle ways from those of standard inflation, differences that future experiments may be able to measure. We are, in all of this, exploring a landscape of ideas that is both intellectually vertiginous and genuinely exciting. The specific models differ from one another in their details and in their predictions. Some will turn out to be wrong. Possibly all of the current proposals are approximations to something better that has not yet been formulated. That is simply how science works at the frontier. The models are tools for thinking, and for making predictions that can be tested, and for understanding which features of the early universe depend on the specific mechanism proposed and which features are more robust. What they share, all of these ideas, from loop quantum cosmology to black hole cosmogenesis to the bounce-driven early acceleration, is a refusal to accept the singularity as the final word. A refusal to let the Big Bang remain an impenetrable wall beyond which nothing can be said. A conviction that the universe's history extends further than classical physics can reach, and that with the right theoretical tools and the right observations, we can begin to trace that history. It is worth reflecting, quietly, on how remarkable this moment in science actually is. For most of human history, the question of what came before the beginning was purely the domain of myth and philosophy and religion. In the 20th century, physics established that the universe had a beginning of some kind, and that the beginning was followed by an evolution that could be described with extraordinary mathematical precision. In the 21st century, physicists are beginning to ask, with real mathematical tools and real observational strategies, whether that beginning was truly a beginning, or whether something came before. The answer is not yet known. But for the first time in history, the question is being asked scientifically. In the universe, patient and vast and indifferent to our timescales, holds its answers somewhere in the patterns of ancient light and the whisper of gravitational waves that have been traveling toward us since before any star was born. We are listening, slowly learning to hear. There is something deeply human about the desire to know not just what exists, but where it came from. We build family trees. We trace rivers to their sources. We dig through layers of rock to find the bones of creatures that lived before memory. And when we turn that same instinct toward the cosmos itself, toward the universe as a whole, we find ourselves confronting possibilities that stretch language nearly to its breaking point. We have been moving gradually outward from the familiar. From the Big Bang as a hot, dense beginning. Through inflation and its unresolved questions. Through the bounce, where the Big Bang becomes not a creation but a transition. And now we arrive at the outermost edge of current theoretical cosmology, a landscape of ideas so expansive, so genuinely strange, that even physicists sometimes pause to absorb what they are actually proposing. We touched earlier on the possibility that our universe originated inside a black hole. Let us sit with that idea a little longer, because it rewards careful attention. When a sufficiently massive star exhausts its fuel, the outward pressure that counteracted gravity for millions of years disappears. The core collapses. If the remaining mass is large enough, nothing stops it. Not electron pressure, not neutron pressure, nothing. The collapse continues past every known threshold, and a black hole forms. From the outside, a black hole is defined by its event horizon, the surface of no return, the boundary beyond which nothing, not even light, can escape back into the surrounding universe. But what happens inside? Classical general relativity gives an answer that most physicists consider unphysical. The matter collapses to a point of infinite density, a singularity, where the equations break down and predictability ends. Loop quantum gravity, as we have seen, replaces that singularity with a bounce. The collapsing matter reaches an extreme but finite density, quantum effects halt the collapse, and an expansion begins. In some models, that expansion does not re-emerge into the parent universe. The geometry of spacetime inside the black hole, under these quantum dynamics, allows for the formation of a new expanding region, causally disconnected from the universe in which the black hole formed, but real, evolving, and potentially vast. Our Big Bang, in this picture, was the interior of a black hole that formed in some prior universe. We are, in a sense, the contents of a gravitational wound in another cosmos. And the early accelerated expansion that we usually attribute to inflation? In some of these models, it emerges naturally from the bounce dynamics, the same quantum repulsion that halted the collapse, producing an initial burst of rapid expansion in the new region. No separate inflaton field required. The acceleration is a consequence of the origin, not an additional mechanism layered on top of it. It is a picture that raises as many questions as it answers. What was the parent universe like? How did it begin? Does the chain extend backward indefinitely, each universe born from a black hole and the one before? These questions do not have agreed-upon answers. But they have the important quality of being, in principle, investigable, because this framework makes predictions, and predictions can be tested. Now let us move to an idea that operates on an even larger canvas. The multiverse. In the framework of eternal inflation, which we encountered earlier, inflation never completely stops everywhere at once. Different regions of the inflating spacetime exit inflation at different times, each becoming a separate expanding universe, a bubble, nucleating within the larger inflationary sea and then evolving independently. Our universe is one such bubble. Around us, potentially separated by distances so vast they have no meaning in ordinary terms, other bubbles exist. Other universes, each with its own history, potentially its own physical constants, its own version of the laws of nature. The bubble multiverse is not a peripheral idea. It emerges naturally and almost inevitably from the mathematics of eternal inflation, and eternal inflation itself emerges from many of the most studied inflationary models. If inflation happened at all, the multiverse may be its unavoidable consequence. But the bubble multiverse is not the only kind of multiverse that serious physics has produced. String theory, with its vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants, suggests a different but related picture. And quantum mechanics itself, in one of its most debated interpretations, suggests that every quantum event that can have multiple outcomes actually has all of them, in branching parallel versions of reality that never interact again after the branching occurs. These are very different proposals with very different mathematical foundations. What they share is the suggestion that our universe, everything we can observe, everything that exists within our cosmic horizon, may be a small part of something incomprehensibly larger. Among the more surprising ideas to emerge from recent theoretical work is the proposal of what is sometimes called the anti-universe, or the CPT-symmetric universe. This framework, developed seriously by a small group of physicists, proposes that our universe has a partner, a mirror universe extending in the opposite direction of time from the Big Bang. Where our universe expands forward in time from that central point, the anti-universe expands backward. Together, they form a symmetric whole, with the Big Bang as the point of symmetry rather than a true beginning. In this picture, the universe has no absolute origin. The Big Bang is not the start of time. It is the center of a time-symmetric structure, with one branch running in each temporal direction. The laws of physics, specifically a combined symmetry involving charge, parity, and time reversal, CPT symmetry, are preserved across the whole structure. Our universe and its mirror image together constitute a single, self-consistent solution to the equations of fundamental physics. This model makes a striking prediction about the composition of the anti-universe. If our universe is dominated by matter, the anti-universe should be dominated by antimatter, not as a separate entity floating somewhere in our space-time, but as the contents of a region of space-time running in the opposite temporal direction. The asymmetry we observe between matter and antimatter in our universe, the fact that matter 1 and antimatter is relatively rare, may, in this view, be explained by the fact that we are in one half of a symmetric structure. The other half carries the antimatter. A related but distinct idea proposes a symmetric matter-antimatter origin, a Big Bang that produced equal amounts of matter and antimatter, which then separated through some mechanism that created distinct regions, one of which became our observable universe. The details of how this separation could have occurred without mutual annihilation are technically challenging, and no fully satisfactory mechanism has been established. But the underlying motivation, to preserve a fundamental symmetry at the origin of the universe, is physically well-grounded and continues to be explored. Let us turn now to string gas cosmology, which approaches the problem of early structure from a completely different direction. String gas cosmology draws directly on the nature of strings and string theory. A fundamental string is not like a point particle. It has extent. It has two qualitatively different modes of motion, winding around compact dimensions of space, and vibrating within them, and these modes have a characteristic duality. When the universe is very small, string winding modes become important in a way that has no analog in conventional physics. And crucially, string theory has a minimum length scale, the string length, below which the concept of distance loses its ordinary meaning. string gas cosmology proposes that the very early universe was not a hot point expanding from a singularity, but a hot, dense gas of strings in a small, possibly toroidal space, held near a fixed size by the balance between winding and momentum modes. This initial phase, sometimes called the Hagedorn phase, was not expanding. It was a kind of string-theoretic equilibrium. The universe then transitioned out of this phase as the winding modes decayed, and the expansion we observe began. In this framework, the large-scale structure of the universe, the patterns of temperature fluctuations that became galaxies, was seeded not by quantum fluctuations stretched by inflation, but by the thermal fluctuations of the string gas during the Hagedorn phase. The prediction this makes about the spectrum of primordial fluctuations is slightly different from that of standard inflation, and future observations of the cosmic microwave background may be able to distinguish between them. String gas cosmology also naturally avoids the singularity problem. Because strings cannot be localized below the string length, and because the string length sets a minimum size for the universe in this framework, the universe never reaches a true zero-size singularity. The beginning is smooth, or at least, smoother than the classical picture. Another approach that has attracted considerable attention is called the matter bounce scenario. In this model, the universe did not begin with inflation. Instead, it began with a contracting phase, during which the seeds of cosmic structure were generated. As the contracting universe became denser, small quantum fluctuations in the distribution of matter were amplified, imprinting a specific pattern on the structure of space. Then, at the point of maximum compression, a bounce occurred, again, driven by quantum gravity effects, and the universe transitioned into the expanding phase we now inhabit. The matter bounce scenario makes a specific prediction about the nature of the primordial fluctuations it generates. In a contracting universe dominated by matter, quantum fluctuations produce what is called a scale-invariant spectrum, the same pattern that inflation produces, and the same pattern that is actually observed in the cosmic microwave background. This is significant. It means the matter bounce is not just an interesting theoretical idea. It can, in principle, explain the same observational evidence that inflation explains, without requiring an inflationary phase at all. Distinguishing between inflation and the matter bounce, and between both of these and string gas cosmology, is one of the central observational challenges in early universe cosmology. Primordial gravitational waves are currently the best hope for making that distinction, because the amplitude and spectral shape of gravitational waves predicted by these different models differ in ways that future experiments may be sensitive enough to measure. What these models also share, the matter bounce, string gas cosmology, loop quantum bounce, and others in the same family, is a determination to avoid the singularity not by ignoring it, but by replacing it with physics that remains well-defined throughout. Some of these models go further and ensure that all physical length scales in the theory remain above the Planck length at all times. Space never becomes so compressed that its quantum nature is overwhelmed by conditions the theory cannot handle. The minimum scale acts as a floor, beneath which the universe simply cannot go. This property has a precise and important name in the mathematics of general relativity and cosmology. These models are described as geodesically complete. A geodesic, in general relativity, is the path that a freely moving object follows through curved spacetime, the natural trajectory of a particle or a light ray in a gravitational field. In classical cosmology, geodesics that you trace backward in time eventually terminate at the singularity. They hit a wall. They end. The universe has a boundary in time, and beyond it, nothing, not even the concept of a trajectory, can be extended. A geodesically complete spacetime has no such boundaries. Every geodesic can be extended indefinitely, both forward and backward in time, without ever hitting a wall. There is no edge. No termination. The universe's history, in both directions, is complete. What this means physically is that there are no hidden beginnings, no moments of creation from nothing, no points where the laws of physics suspend themselves and something inexplicable has to be invoked. The universe, all of it, before and after the bounce, is described by a single, continuous, consistent physical framework. This is what many physicists mean when they say that quantum gravity removes the singularity. They do not just mean that the equations stay finite. They mean that the universe becomes, in the fullest sense, a complete physical object. One whose entire history, however long and however strange, is in principle accessible to description and understanding. We do not yet know which of these pictures, if any, is correct. The matter bounce, string gas cosmology, the black hole origin, the CPT symmetric anti-universe, the loop quantum bounce, these are all serious proposals, each with its own mathematical foundation, its own predictions, its own strengths and unresolved challenges. The field is genuinely competitive. And it is genuinely alive. What unites all of these ideas, beneath their considerable differences, is something more than scientific methodology. It is a kind of philosophical refusal. A refusal to accept that the universe begins in mystery and ends there. A conviction that the cosmos, however extreme its origins, played by rules, and that those rules can be found, and understood, and followed all the way back to wherever the story truly starts. Whether that start is a bounce, a bubble, a black hole, a string gas, or something no one has yet imagined, the search for it is one of the most extraordinary things our species has ever attempted. And on quiet nights, when the world is still, it is worth remembering that the universe you are part of may be far older, far stranger, and far more continuous than any beginning could contain. There is an old question that predates modern cosmology by thousands of years. It appears in ancient Hindu cosmology, in certain strands of Greek philosophy, in the intuitions of thinkers who looked at the cycles of nature, the seasons, the tides, the rising and setting of the sun, and wondered whether the universe itself might follow a similar pattern. Whether the cosmos, like everything within it, might breathe in and out, expand and contract, die and be reborn. For most of the 20th century, this intuition lived at the edges of serious scientific discussion. The Big Bang model was so successful, and the evidence for a singular beginning so compelling, that cyclic ideas were generally treated as poetic rather than scientific. But in the past 2 decades, something has shifted. Several rigorous theoretical frameworks have emerged that give the cyclic universe idea genuine mathematical substance. And while none of them have been confirmed, they have become part of the active conversation in early universe cosmology in a way they simply were not before. Before we explore what these models actually propose, it is worth pausing on a challenge that all cyclic models must face. It is a challenge rooted not in observation but in thermodynamics, specifically in the concept of entropy. Entropy, loosely speaking, is a measure of disorder. The second law of thermodynamics states that in a closed system, entropy tends to increase over time. Things become more disordered, not less. Heat flows from hot to cold. Structures decay. Information spreads and dilutes. This law is one of the most robust in all of physics. It has never been observed to be violated in any macroscopic system. Now apply this to a cyclic universe. If each cycle ends and a new one begins, and if entropy increases throughout each cycle, then the entropy at the start of each new cycle should be higher than at the start of the previous one. Over many cycles, entropy accumulates. And if you trace the sequence of cycles backward in time, you find that earlier cycles must have had lower and lower entropy, implying that the chain of cycles cannot extend infinitely into the past. At some point, there must have been a first cycle, a genuine beginning, with entropy low enough to allow the sequence to start. This is a serious objection, and serious theorists take it seriously. Some cyclic models attempt to include a mechanism that resets entropy at the transition between cycles, some process that dissipates or redistributes the accumulated disorder before the new cycle begins. Whether any such mechanism can be made physically consistent is still an open question. Others accept that the chain of cycles had a beginning, and argue that this is not really a problem. The cyclic structure still describes the vast majority of cosmic history, even if it does not extend infinitely backward. It is a tension that has not been fully resolved. But it has not stopped the development of genuinely creative and testable cyclic frameworks. Perhaps the most elegant of these is the one proposed by the mathematician and physicist Roger Penrose, a framework he calls conformal cyclic cosmology. Penrose begins with a deep observation about the very far future of our universe. As the universe continues to expand and accelerate, driven by dark energy, it will eventually reach a state in which nearly all matter has either been consumed by black holes or decayed into radiation. The black holes themselves will gradually evaporate through Hawking radiation over almost incomprehensibly long timescales. And in the very far future, the universe will consist almost entirely of a dilute bath of photons and other massless or nearly massless particles, expanding through an ever larger space. Here is the key insight. Massless particles do not experience time in the ordinary sense. A photon, traveling at the speed of light, has no proper time along its trajectory. And because of a mathematical property called conformal symmetry, a symmetry that relates structures of different sizes but the same shape, the geometry of this extremely dilute, far future universe has a deep mathematical similarity to the geometry of the very early universe just after the Big Bang. Penrose proposes that these two geometries, the far future of one cosmic cycle and the early moments of the next, can be mathematically identified with each other. The end of one universe is the beginning of the next, not metaphorically but in a precise geometric sense. The boundary of one aeon, as Penrose calls each cosmic cycle, is smoothly joined to the beginning of the following aeon. The universe does not collapse and re-explode. It simply continues, crossing a geometric boundary that is invisible to the massless particles that traverse it, but which marks a complete reset of cosmic scale. What makes conformal cyclic cosmology genuinely scientific rather than merely speculative is that it makes observational predictions. Specifically, it predicts that events in the previous aeon, most notably the mergers of supermassive black holes, which release enormous amounts of energy, should leave faint but detectable imprints on the cosmic microwave background of the current aeon. These imprints, in Penrose's model, would appear as subtle circular patterns in the CMB, concentric rings of slightly anomalous temperature, the echoes of catastrophic events in a universe that existed before our own. Penrose and his collaborators have claimed to find evidence of these patterns in existing CMB data. The statistical significance of these claims has been debated. Other researchers have argued that the patterns can be explained by the known statistical properties of the CMB without invoking a prior aeon. The question has not been definitively settled, and it remains an active area of analysis. But the important point is that the question can be asked scientifically. There is data. There are predictions. There is a community of researchers examining the evidence. Whatever the eventual verdict, conformal cyclic cosmology has taken an ancient intuition and transformed it into a falsifiable scientific hypothesis. That is a remarkable achievement. The hot spots and anomalies that Penrose points to as potential traces of prior eons are themselves fascinating objects. The idea that we might be looking at the gravitational echoes of black hole mergers from a previous universe, events that occurred before time, as we normally count it, even began, is one of the most haunting propositions in all of modern science. If it is true, then the cosmic microwave background is not just a window onto the earliest moments of our universe. It is a palimpsest, a document written over, with faint traces of an earlier text still visible beneath. Even if conformal cyclic cosmology turns out to be incorrect, the idea that the end of one universe resembles the beginning of the next has a deep appeal that goes beyond aesthetics. It suggests a kind of cosmic continuity, a universe that does not require an absolute beginning because it is always, in some sense, continuous with what came before. Now let us turn to the more classical cyclic models, the ones that operate not through Penrose's conformal geometry but through the more intuitive idea of expansion followed by contraction. The original cyclic universe model, sometimes called the oscillating universe, was proposed in various forms in the early and middle 20th century. In its simplest version, the universe expands from a Big Bang, reaches a maximum size, and then contracts under gravity back toward a Big Crunch, a final state of extreme density that mirrors the Big Bang. At the moment of maximum compression, another Big Bang occurs, and a new cycle begins. The universe oscillates indefinitely, with each cycle, each bang and crunch, lasting some finite duration. This picture is intuitively appealing in many ways. It avoids the philosophical discomfort of an absolute beginning. It avoids the equally uncomfortable prospect of an absolute end. And it preserves a kind of cosmic permanence. The universe is always there, always evolving, never requiring a creation from nothing. but the classical oscillating model ran into significant difficulties. The entropy problem we discussed earlier is one of them. Each cycle should be longer and larger than the previous one, implying that the sequence cannot extend infinitely backward. And the discovery that the expansion of the universe is accelerating, driven by dark energy, made the simple gravity-driven turnaround seem impossible under known physics. A universe dominated by dark energy does not reverse course and collapse. It expands forever, faster and faster. More sophisticated cyclic models have been developed to address these difficulties. One of the most carefully constructed is the ekpyrotic cyclic model, associated with Paul Steinhardt and Neil Turok, among others. In this framework, our universe is a three-dimensional surface, a brain, in the language of string theory, embedded in a higher dimensional space. A second brain exists nearby, also embedded in this higher dimensional space, separated from ours by a small but non-zero distance. The two brains interact through gravitational forces mediated across the gap between them. Over an enormously long period, far longer than the current age of our universe, the brains slowly drift apart, the universe expands and cools, and matter and energy become increasingly dilute. This corresponds to the slow expansion phase of the cycle. Then, gradually, the brains are drawn back toward each other by the interbrain potential. They accelerate. And eventually, they collide. That collision is the Big Bang of the next cycle. The kinetic energy of the collision heats the brains to an enormous temperature, fills them with matter and radiation, and the familiar expanding universe begins again. The entropy accumulated in the previous cycle is distributed across the vast, dilute space of the far future brain, effectively resetting the conditions for the new cycle to begin with low entropy, addressing the thermodynamic objection, at least in principle. The ekpyrotic model also generates a spectrum of density fluctuations during the slow contraction phase, fluctuations that may produce a pattern in the cosmic microwave background distinguishable from that produced by inflation. Again, the gravitational wave signature is a key discriminator. Ekpyrotic models generally predict a very low amplitude of primordial gravitational waves, significantly lower than many inflationary models, and future experiments measuring the CMB polarization should be sensitive enough to test this prediction. What is particularly noteworthy about the ekpyrotic and related cyclic models is that they take seriously the idea of a cosmos that undergoes repeated cycles without an absolute beginning, or at least, without requiring one in any practically meaningful sense. Each cycle begins with a bang and ends with either a crunch or a collision. Each new cycle inherits some features of the previous one and resets others. The universe is not created from nothing. It transitions, over and over, through phases of expansion and contraction, carrying its own history forward in ways that may or may not leave observable traces. This avoidance of absolute nothingness is not merely philosophical comfort. It is, for many physicists, a genuine theoretical virtue. A universe that begins from nothing requires an explanation for why it begins at all, and why it begins with the particular properties it has. A universe that transitions from a prior state requires only an explanation for the transition mechanism, a significantly less demanding problem, and one that physics is at least partially equipped to address. Some of the slower cyclic models, those in which the transition from expansion to contraction happens over very long timescales, have the additional appealing feature of explaining why the current acceleration of the universe need not be permanent. In these models, dark energy is not a fixed cosmological constant but a slowly evolving field that changes sign over cosmic time, eventually driving contraction rather than expansion. The acceleration we observe today is a phase, a very long phase, to be sure, measured in tens of billions of years, but a phase nonetheless, destined to eventually reverse. Whether this is true, and whether any of the cyclic models captures something real about the universe's ultimate nature, remains genuinely unknown. Cosmology has not yet delivered a verdict. The data from next-generation CMB experiments, from gravitational wave observatories, from surveys of the large-scale structure of the universe, all of this will gradually narrow the field of viable possibilities. Some models will be ruled out. Others will gain support. And the picture of the universe's past and future will continue to sharpen. What strikes me, thinking about all of these ideas together, is how profoundly they change the emotional register of cosmology. The standard narrative, universe begins, expands, eventually ends, has a certain tragic arc to it. A single story, with a beginning and an end, surrounded on both sides by nothing. The cyclic models offer something different. A universe that persists, that renews, that carries its history through the most extreme transitions imaginable and emerges, each time, into a new era of possibility. We do not know if that is the universe we live in. But the fact that it might be, the fact that the cosmos we inhabit may be part of an ongoing story with no first page and no last, is one of the quietly extraordinary gifts of modern theoretical physics. The night sky you look up at may not be the ceiling of a single, solitary universe. It may be one panel in a tapestry that has no edge. Physics, at its most ambitious, is not content to describe the universe as it is. It wants to understand why it could not have been otherwise, why the laws are what they are, why the initial conditions were what they were, why the universe we observe has the specific character it is rather than some other character entirely. And when a successful theory leaves questions unanswered, the most intellectually honest response is not to paper over them, but to take those questions seriously and look for something better. Inflation has been the dominant framework in early universe cosmology for more than 4 decades. It has earned that position through genuine explanatory success. But the questions it leaves open are real, and the community of physicists working on early universe cosmology has never stopped asking them. The result is a landscape of alternatives and extensions, some modest modifications of the standard picture, some radical departures from it, that collectively represent one of the most creative periods in the history of theoretical cosmology. We spent considerable time in our last exploration with cyclic models, frameworks in which the universe undergoes repeated cycles of expansion and contraction rather than a single trajectory from a unique beginning. And we saw how these models, at their most developed, can reproduce some of the same observational successes that inflation achieves. But we also encountered a persistent challenge, the problem of entropy accumulation across cycles. It is worth understanding this problem a little more carefully, because the ways in which different cyclic models attempt to solve it reveal something important about what these theories are actually proposing. In any cyclic model, each cycle of cosmic evolution generates entropy. Stars form and radiate. Black holes grow and eventually evaporate. Structure forms and dissolves. All of these processes are irreversible in the thermodynamic sense. They increase the total entropy of the universe. If cycles simply follow one after another without any mechanism to address this accumulation, then each successive cycle inherits a higher entropy than the one before. And as we trace backward in time, the entropy of earlier cycles becomes lower and lower, implying that the chain of cycles cannot extend infinitely into the past. There must have been a first cycle, a genuine beginning with anomalously low entropy, which rather defeats the purpose of a cyclic model. Several different approaches to this problem have been developed, each with its own strengths and its own controversies. One of the most physically motivated solutions is entropy dilution through expansion. In models where each cycle reaches an enormous size before the transition to contraction, the entropy generated during that cycle is spread across a correspondingly enormous volume. When the new cycle begins, the entropy density, entropy per unit volume, can be very low, even if the total entropy is high. A new cycle beginning from this diluted state has effectively reset its entropy density to a value low enough to allow structure formation and the development of complexity. The universe looks, locally, like it is starting fresh. This is an elegant idea, but it faces a conceptual objection that some physicists consider decisive. If each cycle expands to a vast size to dilute its entropy, and if the new cycle begins from that vast, dilute state, then in what sense is the new cycle a repetition of the previous one? The initial conditions of each cycle are not truly reset. They are inherited from the far future state of the previous cycle, which is itself the product of all the entropy generated throughout that cycle's history. The cycles are not identical. They are, in a thermodynamic sense, getting progressively more dilute, more spread out, more different from their predecessors. Whether this counts as a genuine solution to the entropy problem, or merely a reformulation of it, is a point of ongoing debate. There is also a deeper question lurking here, one that touches on the foundations of statistical mechanics as much as cosmology. The low entropy of the early universe is one of the most significant unexplained facts in all of physics. Why was the Big Bang a low-entropy event? Why did the universe begin in such a highly ordered state, when the overwhelming majority of possible initial conditions would have been disordered? Inflation does not really answer this question. It assumes low-entropy initial conditions and then evolves them forward. Cyclic models that rely on entropy dilution shift the question rather than answering it. And models that posit a genuine beginning to the cyclic sequence simply relocate the mystery to that first cycle. Some of the most carefully constructed cyclic models attempt to address this by demonstrating that the cyclic dynamics naturally drive the universe toward what is called an attractor state. An attractor, in the language of dynamical systems, is a configuration toward which a wide range of different initial conditions evolve over time. If a cyclic universe has an attractor, then regardless of the detailed conditions at the start of any given cycle, the universe gradually converges toward a characteristic state, a kind of dynamical equilibrium that the cycles approach but perhaps never quite reach. The appeal of an attractor solution is significant. If the universe naturally evolves toward a specific cyclic pattern regardless of its initial conditions, then the question of what those initial conditions were becomes less pressing. The current state of the universe does not depend sensitively on the details of the very first cycle, or even on whether there was a first cycle at all. The attractor does the explanatory work that a carefully specified beginning would otherwise have to do. Whether specific cyclic models actually have attractors with the right properties is a detailed technical question. In some models, the attractor behavior has been demonstrated mathematically, at least in simplified settings. In others, it remains an aspiration rather than a proven feature. And the question of whether the attractor is stable against the kinds of perturbations that a real universe would experience, quantum fluctuations, irregular matter distributions, the effects of structure formation, is still being investigated. What is clear is that no current cyclic model has completely solved the entropy problem to everyone's satisfaction. This is not a reason to dismiss these models. It is a reason to continue working on them. The entropy problem is a genuine physical puzzle, and any cosmological framework that claims to describe the universe's long-term evolution must eventually provide a satisfying account of it. Some cyclic models have faced an additional criticism that cuts even deeper than the entropy question. In certain formulations, careful analysis reveals that while the model describes many cycles extending into the future, tracing it backward in time eventually leads to a state that cannot be described within the cyclic framework itself, a genuine beginning, despite the model's intent to avoid one. The model reintroduces the very thing it was designed to eliminate. This is not always a fatal flaw. Sometimes it simply means that the cyclic behavior is future eternal but not past eternal. The universe will cycle indefinitely going forward, but had some kind of origin in the finite past. This is a scientifically coherent position, and it does not necessarily undermine the model's value as a description of cosmic evolution. But it does mean that the question of the absolute beginning has not been dissolved. It has been deferred. The honest scientific response to all of this is to hold these frameworks with appropriate tentativeness, to appreciate their genuine insights while remaining clear-eyed about their unresolved difficulties. This is precisely what the most careful researchers in the field do. And it is this same spirit of honest inquiry that has driven the development of alternatives to inflation that operate outside the cyclic framework entirely. We touched earlier on some of these alternatives: the matter bounce, string gas cosmology, quadratic quantum gravity. But there is a broader category of approaches that deserves its own careful attention. These are the models that do not simply propose a different mechanism for the early universe, but question whether the framework of Einstein's general relativity itself, the geometric theory of gravity that underlies nearly all of modern cosmology, is the right foundation for describing the universe at the largest scales and the most extreme conditions. Modifying gravity is not a casual undertaking. General relativity is one of the most precisely tested theories in all of science. It has passed every experimental test it has been subjected to, from the bending of light around the sun to the orbital decay of binary pulsars to the direct detection of gravitational waves. Any modification of gravity must reproduce these successes exactly, while producing different behavior only in regimes where general relativity has not yet been tested, at extremely high energies, at extremely large scales, or in the very early universe. This is a demanding constraint, but it is not an impossible one. And the motivation for trying is real, because general relativity, for all its triumphs, does have problems. At the very small scales of the early universe, it produces singularities. At the very large scales of the current universe, it requires the introduction of dark energy, a mysterious component with no known physical identity, to account for the observed acceleration of expansion. These are not failures in the sense of contradicting observations. They are gaps in understanding, places where the theory gestures towards something it cannot itself explain. Modified gravity theories attempt to fill some of these gaps by altering the equations of general relativity in specific, controlled ways. Some add higher-order terms to the gravitational action, mathematical expressions that become important only at extreme curvatures, such as those of the early universe or the interior of black holes, but are negligible under ordinary conditions. These higher-order modifications can change the behavior of the universe dramatically in the Planck epoch, potentially removing the singularity and altering the dynamics of the very early expansion in ways that are observationally distinguishable from standard inflation. Others modify gravity on large scales, changing the way gravity behaves at cosmological distances in order to explain dark energy without invoking a new field or a cosmological constant. These large-scale modifications have implications for structure formation, for the growth of galaxy clusters, for the relationship between matter distribution and gravitational lensing, all things that can, in principle, be measured. The range of modified gravity theories that have been seriously explored is considerable. Some extend general relativity by including a scalar field coupled to the curvature of spacetime, a class of theories with roots going back to the mid-20th century, and which have been revived and refined many times since. Others modify the geometric foundation more radically, replacing the Riemannian geometry of general relativity with a different mathematical structure that has different symmetries and different equations of motion. What is striking about this proliferation of alternatives is that it reflects not a crisis in physics, but a maturation. The standard model of cosmology is successful enough that its remaining problems stand out in sharp relief. And the precision of current and near-future observations is high enough that these alternatives are not just theoretically interesting, they make predictions that can actually be tested. The parameter space of modified gravity theories is being systematically explored and constrained by data from galaxy surveys, CMB experiments, and gravitational wave detectors. Some of these theories will survive that process of testing. Most will not. That is how science is supposed to work. The theories that survive will be those that explain everything the standard model explains, while also resolving some of the puzzles it cannot. And those theories, if and when they emerge, will not just be refinements of our current understanding. They will be genuinely new ways of thinking about what gravity is, what spacetime is, and what the universe is made of at its most fundamental level. We are, in this sense, living through an extraordinary period. The tools to distinguish between these competing visions of the early universe, the experiments, the observations, the computational methods, are either already in hand or being built right now. Within the coming decades, the landscape of viable cosmological models will narrow considerably. Questions that have been genuinely open for 40 years may approach resolution. And even as some questions close, new ones will open. They always do. The universe is not a puzzle with a fixed number of pieces that can eventually be assembled into a final picture. It is something more dynamic than that, a conversation between observation and imagination that generates new depth at every level of understanding. The modifications to gravity being explored today may reveal, in the end, that space and time are not the fundamental ingredients of reality but emergent properties of something deeper still. Something for which we do not yet have the right language, let alone the right equations. That possibility, that the deepest level of physical reality remains genuinely unknown, is not cause for anxiety. It is the most honest description of where we stand. And for a species that has only been asking rigorous scientific questions for a few centuries, it seems about right. There is a great deal more to discover. The universe has been patient with us so far. It will wait a little longer. The history of science is not a straight line. It moves in spirals, in fits and starts, in unexpected directions. A framework that seems settled for decades can suddenly find itself questioned not from outside science, but from within it, by researchers who have looked carefully at the assumptions built into the standard picture and asked, with genuine intellectual seriousness, whether those assumptions are actually necessary. Most of the ideas we have explored so far, loop quantum cosmology, the matter bounce, string gas cosmology, ekpyrotic cycling, accept the broad framework of modern physics and modify specific aspects of it. They keep general relativity as a foundation while extending it into quantum regimes. They keep the expanding universe as a basic fact while questioning what drove that expansion in its earliest moments. They are, in the language of science, modifications from within the paradigm. But there is another category of approaches, smaller in number, more controversial in status, but not without serious proponents, that question more fundamental aspects of the standard picture. Some of these ideas modify the constants of nature themselves. Others reinterpret the observational evidence in ways that do not require expansion at all. And at least one framework goes deeper than any of these, questioning not just what happened at the beginning of the universe, but what space and time fundamentally are. Let us begin with the most conservative of these departures, and work outward from there. The constants of nature, the gravitational constant, the speed of light, the fine structure constant that governs electromagnetic interactions, are called constants because, as far as every experiment we have ever conducted can determine, they do not change. They have the same values here as they do in distant galaxies. They have the same values now as they did when the light from ancient quasars was emitted billions of years ago. But this constancy has only been tested over a finite range of conditions and timescales. And some theorists have explored what happens if you allow the possibility that certain constants, particularly the gravitational constant, may have taken different values in the very early universe. Not random different values, but values governed by some deeper dynamical law that drove them toward their current levels over cosmic time. If the gravitational constant was different in the early universe, the entire dynamics of the Big Bang and the formation of structure would have been different. The balance between expansion and gravitational collapse that determined which density fluctuations grew into galaxies and which were smoothed out would have been struck differently. The timing and character of nucleosynthesis, the production of hydrogen, helium, and lithium in the first minutes, would have been altered. A theory proposing variable constants must, therefore, reproduce all of the observational successes of standard cosmology while making different predictions in the early universe regime. That is a stringent test, and most such theories have struggled to pass it completely. Nevertheless, the idea has not been abandoned. In part, this is because some theoretical frameworks that are otherwise well-motivated, certain versions of scalar tensor gravity, for instance, which generalize general relativity by coupling a scalar field to the gravitational interaction, naturally produce a varying gravitational constant as a consequence. The variation is not put in by hand. It emerges from the structure of the theory. Whether nature actually chose such a theory is an empirical question, and current observational bounds on the variation of the gravitational constant are extremely tight. But the tight bounds are themselves informative. They constrain the parameter space of these theories in ways that tell us something about the structure of any more fundamental theory that might underlie them. A more radical departure from the standard picture involves not varying constants but a completely different interpretation of what the universe is actually doing. In the standard model, the universe is expanding, galaxies are receding from each other because the space between them is growing. This expansion is inferred primarily from the redshift of light from distant galaxies. The further away a galaxy is, the more its light is shifted toward longer, redder wavelengths. In the standard picture, this redshift is a direct consequence of cosmic expansion. Light stretches as the space through which it travels stretches. But what if the redshift has a different explanation? Some researchers have proposed that light loses energy gradually as it travels across cosmic distances, not because space is expanding, but because of some intrinsic property of the photon or of the medium through which it travels. This class of ideas is known, collectively, as tired light. In a tired light universe, the cosmos need not be expanding at all. It could be static, or nearly so, with the redshift of distant galaxies explained by the cumulative energy loss of photons on their long journeys. Tired light ideas have a long history. They were taken seriously in the early decades of observational cosmology, before the evidence for an expanding universe became overwhelming. Today, they are considered inconsistent with multiple independent lines of evidence: the observed time dilation of supernova light curves, the specific pattern of temperature fluctuations in the cosmic microwave background, the statistics of galaxy clustering, all of which are naturally explained by an expanding universe and very difficult to explain in a static tired light framework. Most cosmologists regard tired light as effectively ruled out. But it is worth understanding why these ideas keep being revisited. The persistence of tired light proposals, despite their difficulties, reflects a genuine desire to question whether the inference from redshift to expansion is as airtight as it is usually presented. And occasionally, The act of taking an alternative seriously enough to test it rigorously leads to new insights, even when the alternative itself is ultimately rejected. More seriously motivated are the proposals sometimes grouped under the heading of non-expanding universe models with modified physics. These are not simply tired light ideas recycled. They are attempts to build internally consistent cosmological frameworks in which the universe does not expand in the standard sense, but in which the apparent observations of expansion are explained through modifications to the underlying physics, changes to how distances are measured, or how light propagates, or how the geometry of spacetime is defined. Some of these models draw on the mathematical observation that general relativity has a conformal symmetry, a symmetry under risk scaling of distances, that is not fully exploited in the standard cosmological framework. If this symmetry is made physically real rather than merely mathematical, then what looks like an expanding universe from one perspective looks like a universe with shrinking atoms from another. The galaxies are not moving apart. The rulers we use to measure distances are getting shorter, at a rate that makes distances appear to increase. This sounds like a trivial reinterpretation, but it is not entirely. Different physical assumptions about what is truly constant, the atomic scales or the cosmological scales, lead to different predictions about observations, particularly in regimes where the two perspectives cannot be trivially exchanged. Some researchers have argued that the shrinking atoms picture has advantages in explaining certain observations, particularly those related to the large-scale uniformity of the universe, without requiring inflation. Others have argued that the two pictures are physically equivalent and the choice between them is purely conventional. The debate is technically subtle and has not been resolved. But it points to something important. Our interpretation of cosmological observations depends on assumptions that are usually made implicitly, and making those assumptions explicit is always a worthwhile exercise. Cold Big Bang models represent a different departure from the standard picture. In the conventional hot Big Bang, the universe begins at an enormous temperature and cools as it expands. In cold Big Bang models, the universe begins at a much lower temperature, cold or nearly cold, and the energy that drives subsequent evolution comes not from thermal radiation but from some other source, such as the quantum properties of fields that were present from the beginning. The interest in cold initial conditions stems in part from the philosophical appeal of starting from the simplest possible state, not a roiling, ferociously hot plasma, but something quiet, nearly empty, and quantum mechanical in character. If the universe began cold, the process by which structure formed, galaxies, clusters, voids, must have worked quite differently from the standard picture, because the thermal radiation that plays such a central role in standard structure formation would not have been present in the same way. Some cold Big Bang models generate structure through mechanisms that do not involve inflation and do not involve the acoustic oscillations in the primordial plasma that are so central to the standard account. Whether these mechanisms can reproduce the detailed pattern of the cosmic microwave background and the observed large-scale structure of the universe is a quantitative question that requires careful calculation. The results, in most cases, have not matched observations as well as the standard model does. But the exercise of working through these alternatives has clarified which features of the standard picture depend on specific assumptions and which features are more robust. Group field theory occupies a very different position in this landscape. It is not a minor modification of the standard picture. It is a fundamental rethinking of what spacetime is and how it came to exist. In general relativity, spacetime is a continuous, smooth geometric object, a four-dimensional manifold with a metric that tells you distances and angles. This geometry is the arena in which all physics takes place. It is modified by the presence of matter and energy, but it is always, in the standard picture, a background structure of some kind. Even in the quantum theories of gravity we have discussed, space is typically assumed to have some structure, loops, strings, branes, that constitutes the fundamental fabric. Group field theory questions this assumption at its root. In this framework, spacetime is not fundamental. It is emergent. It does not exist at the deepest level of physical description. Instead, it arises from the collective behavior of more fundamental quantum degrees of freedom, abstract mathematical objects that have no spatial or temporal location in the ordinary sense, because space and time have not yet come into existence. The analogy often used is thermodynamics. Temperature, pressure, and volume are not fundamental properties of matter. They are emergent descriptions that become meaningful when you have a large number of particles behaving collectively. A single atom does not have a temperature. Temperature is a property of ensembles. Similarly, in group field theory, spacetime geometry is a property of ensembles of the fundamental quantum objects. It emerges from their collective behavior in a regime where large numbers of them are present and interacting. In the early universe, when the universe was extremely small and dense, the number of these fundamental quanta may have been small enough that the emergent spacetime description breaks down. There was no smooth spacetime. There was no geometry in the ordinary sense. There was something more primitive, a quantum state of the fundamental degrees of freedom from which spacetime would eventually condense, much as a crystal condenses from a liquid when the temperature drops below a critical point. The Big Bang, in this picture, is not an event that happened in spacetime. It is the moment at which spacetime itself came into being, a phase transition from the pre-geometric quantum regime to the geometric universe we now inhabit. There is no singularity, because there is no spacetime in which a singularity could occur. The singular behavior of the classical equations is replaced by a smooth quantum emergence, a transition from a state without geometry to a state with it. This is conceptually the deepest of all the alternatives we have discussed. It does not just modify what happened at the beginning of the universe. It questions whether the beginning was an event in time at all, since time itself is emergent in this framework. The question what came before the Big Bang is not answered by pointing to a prior state and a prior time. It is answered by describing the pre-geometric quantum state from which both space and time condensed. Group field theory is an active area of mathematical physics, with a growing body of technical results. Some of these results have made contact with loop quantum cosmology. The two frameworks share conceptual and mathematical roots, and there are known correspondences between them in certain limits. But group field theory, in its full form, is a more ambitious and less fully developed framework. Many of its key technical challenges remain unsolved. The conditions under which the classical spacetime of general relativity emerges from the quantum degrees of freedom have been partially worked out, but not completely. The cosmological implications, what specific predictions does this framework make about the early universe, are still being derived. What group field theory offers, even in its current incomplete form, is a vision. A vision of a physics in which the question of what came before the Big Bang is not a question about what existed in a prior time, but a question about what the pre-geometric quantum state was like, and how it transitioned into the universe of space and time and matter that we now inhabit. It is a vision that requires letting go of some very deep intuitions about what it means for something to exist, about what time is, about what it means for an event to have a location. These intuitions are not wrong, exactly. They are appropriate for the universe we experience, the universe in which spacetime is a good emergent description. But they may simply not apply at the level where physics is ultimately happening. There is something both vertiginous and peaceful about that possibility. Vertiginous because it means the deepest reality may be genuinely alien to everything we can directly experience or imagine. Peaceful because it suggests that the universe is not built on a foundation of arbitrary beginnings and inexplicable singularities, but on something more fundamental, something that may, in the end, be as natural and inevitable as the laws that govern the motion of planets and the fusion of stars. We have traveled a long way from the Big Bang as a simple starting point. We have traced the questions that starting point generates all the way down to the level of spacetime itself, to the possibility that space and time are not the bedrock of reality but a kind of crystallization from something deeper, something pre-geometric, something for which we are still finding the right language. And the journey is not over. It is barely, in the longest view, beginning. When you look at the history of physics, one pattern emerges again and again. A theory works brilliantly within its domain. It makes precise predictions. It passes every test it is given. And then, at some boundary, some extreme of scale or energy or condition, it begins to fail. Not catastrophically, not all at once, but in ways that are quiet and specific and deeply informative. The failure points are not embarrassments. They are invitations. They mark the places where a deeper theory is waiting to be found. General relativity fails at the singularity. Quantum field theory, in its standard form, fails to incorporate gravity at all. And the two theories together, the most successful frameworks in the history of physics, each tested to extraordinary precision in its own domain, are fundamentally incompatible when applied simultaneously to the same system. They disagree about the nature of reality at the most basic level. General relativity describes a smooth, continuous, deterministic universe. Quantum mechanics describes a granular, probabilistic, observer-dependent one. Somewhere between these two descriptions, the truth lies. And the search for that truth is what the field of quantum gravity is about. It is a field with many approaches, many schools of thought, and no settled consensus. But it is not a field without structure. Over the decades, the various approaches have been organized, compared, and classified in ways that help clarify what each is actually attempting and what the key differences between them really are. One of the most useful organizing distinctions is the difference between what are sometimes called top-down and bottom-up approaches to quantum gravity. These terms describe the direction from which a theory approaches the problem. A top-down approach starts from a large, overarching theoretical framework, often one motivated by considerations of mathematical consistency, unification, or elegance, and derives the physics of gravity and spacetime as consequences of that larger framework. The starting point is a grand structure, and general relativity emerges from it in some appropriate limit, the way thermodynamics emerges from statistical mechanics. A bottom-up approach starts from general relativity itself and asks how to quantize it, how to apply the principles of quantum mechanics directly to the geometric theory of gravity, without first embedding it in a larger framework. The starting point is the known physics, and the goal is to extend it into the quantum regime in the most direct and conservative way possible. String theory is the most developed and most studied top-down approach. It begins with the assumption that the fundamental constituents of reality are not point particles but one-dimensional objects, strings, whose different vibrational modes correspond to different particles and forces. Gravity emerges naturally in string theory as a consequence of the string spectrum. The graviton, the hypothetical particle that mediates gravitational interactions, appears automatically, without being put in by hand. And string theory is, in its various formulations, ultraviolet complete. It remains mathematically consistent at arbitrarily high energies, without producing the uncontrolled infinities that plague simpler attempts to quantize gravity. The cost of this consistency is significant. String theory requires extra dimensions of space beyond the 3 we observe, typically 6 or 7 additional dimensions, compactified at scales far too small to detect with current technology. It predicts an enormous landscape of possible vacuum states, each corresponding to a different set of physical laws. And despite decades of intensive mathematical development, it has not yet made a prediction that has been confirmed by experiment and that could not have been made without it. This last point is the most important scientific concern about string theory, and serious string theorists acknowledge it. The theory has produced extraordinary mathematics, insights that have found applications in condensed matter physics, in the study of black hole thermodynamics, in number theory, but its connection to observable physics remains, for now, largely indirect. Loop quantum gravity is the most developed bottom-up approach. Rather than embedding gravity in a larger framework, it applies the techniques of quantum mechanics directly to general relativity. The result, as we have explored in earlier segments, is a description of spacetime as a discrete quantum structure, a network of spin network states that describe the quantum geometry of space at the Planck scale. Time evolution in this framework produces what are called spin foams, quantum histories of spatial geometry, analogous in some ways to the Feynman path integrals of ordinary quantum field theory. Loop quantum gravity does not require extra dimensions. It does not require supersymmetry. It makes minimal assumptions beyond general relativity and quantum mechanics themselves. And it has produced concrete results in cosmology, the replacement of the Big Bang singularity with a quantum bounce, the deterministic evolution through that bounce, and specific predictions about the spectrum of primordial gravitational waves. The challenge for loop quantum gravity is different from string theory's challenge. the mathematical consistency of the framework in its full form, not just in the simplified cosmological setting but in its complete four-dimensional version, is still being established. In the recovery of smooth, classical general relativity from the discrete quantum structure in the appropriate limit, while understood in broad outline, requires technical work that is still ongoing. Group field theory, as we discussed in the previous segment, sits in an interesting position relative to both of these. It shares mathematical roots with loop quantum gravity. The fundamental variables are related, but it frames the problem differently, describing spacetime as emergent from the collective behavior of quantum degrees of freedom rather than as a quantized version of classical geometry. In this sense, it has elements of both a top-down and a bottom-up approach, or perhaps transcends the distinction. Asymptotic safety represents a different bottom-up strategy. Rather than discretizing spacetime or embedding gravity in a larger framework, asymptotic safety asks whether quantum gravity might be a well-defined quantum field theory after all, not in the naive sense, which produces uncontrolled infinities, but in a more subtle sense involving a non-trivial ultraviolet fixed point. An ultraviolet fixed point is a configuration of the theory's parameters toward which the theory flows as you probe shorter and shorter distances. If gravity has such a fixed point, then the quantum field theory of gravity is well defined at all scales. It is UV complete, even without extra dimensions or strings or any of the other exotic machinery that string theory requires. Asymptotic safety has been investigated seriously since the work of Steven Weinberg in the late 1970s, and the evidence for the existence of the relevant fixed point has accumulated considerably over the past 2 decades through increasingly sophisticated calculations. Whether it truly exists, and whether the theory at the fixed point describes something physically sensible, are questions that are still being answered. But asymptotic safety has the significant advantage of economy. It modifies general relativity as little as possible while still achieving UV completeness, and it makes predictions about the running of gravitational couplings at high energies that could, in principle, leave observable signatures in the early universe. Non-commutative geometry takes yet another approach, modifying not just the dynamics of gravity but the underlying mathematical structure of spacetime itself. In ordinary geometry, the coordinates of spacetime commute. The x-coordinate and the y-coordinate can be specified independently, and the order in which you measure them does not matter. In non-commutative geometry, this commutativity is abandoned. Space and time coordinates become operators that do not commute, in direct analogy with the position and momentum operators of quantum mechanics. This non-commutativity introduces a fundamental minimum length scale into the geometry, a Planck scale graininess that modifies physics at extreme energies and potentially resolves the singularities of classical gravity. Non-commutative geometry has a rich mathematical structure, developed extensively by the mathematician Alain Connes, and it has found applications across several areas of physics, including the derivation of the standard model of particle physics from geometric principles. Its cosmological implications have been explored, particularly in the context of the early universe, where the modified dispersion relations that arise from non-commutativity can affect the spectrum of primordial fluctuations. What all of these frameworks share, despite their considerable differences, is the goal of unifying the physics of the very small and the physics of the very large, of finding a single consistent description that works at all scales and all energies, including the extreme conditions of the early universe. And they share something else: a growing insistence on the importance of testable predictions. This insistence is, in some ways, a response to criticism. For a significant period, quantum gravity research, particularly string theory, was questioned on the grounds that it was producing beautiful mathematics without generating predictions that experiments could test. That criticism was not entirely fair, but it was not entirely unfair either. And the field as a whole has responded by placing greater emphasis on the connection between theoretical frameworks and observable consequences. The cosmic microwave background is the most important observational target. Its precise pattern of temperature fluctuations and polarization carries information about the very early universe that different quantum gravity frameworks predict differently. The amplitude and spectral tilt of primordial gravitational waves, the B-mode polarization signal in the CMB, is a particularly discriminating observable. Different models make different predictions about this signal, and next-generation CMB experiments are being designed with the sensitivity to detect or rule out these predictions. Primordial gravitational waves themselves, detected directly rather than through their CMB imprint, are another target. Future space-based gravitational wave detectors, probing frequency ranges inaccessible to current instruments, may be sensitive to the backgrounds of gravitational waves produced in the early universe. The spectrum and amplitude of these backgrounds depend on the details of early universe physics in ways that could distinguish between, for instance, asymptotic safety and loop quantum gravity, or between inflationary and bounce cosmologies. Some frameworks predict specific modifications to the propagation of gravitational waves across cosmological distances, small but potentially measurable changes in the speed of gravity, or in the rate at which gravitational wave amplitude decays with distance. These predictions can be tested by comparing gravitational wave observations with electromagnetic observations of the same events. The multi-messenger astronomy inaugurated by the detection of a neutron star merger in 2017 opened this observational window, and it will grow considerably more powerful as gravitational wave detector sensitivity improves. There is also the possibility, speculative but taken seriously by some researchers, that quantum gravity effects might leave signatures in the statistics of high-energy cosmic rays, or in subtle modifications to the dispersion of light from distant gamma-ray bursts, or in the detailed thermodynamics of black holes. Each of these represents a potential window onto physics at the Planck scale, opened not by building a Planck energy accelerator, which is not remotely feasible, but by using the universe itself as a laboratory. The universe has, after all, already performed the Planck scale experiment. It did so in the first moments of its existence. And the results of that experiment are encoded in the structures we can observe today, in the CMB, in the gravitational wave background, in the distribution of matter across cosmic scales. Reading those results accurately requires the right theoretical framework. And developing that framework is the central challenge of quantum gravity research. What has become increasingly clear, across all of these approaches, is that the early universe's structure does not necessarily require exotic new ingredients. Some of the most promising models, asymptotic safety, Certain formulations of loop quantum cosmology, the quadratic quantum gravity framework we discussed earlier, generate the features of the early universe from the internal dynamics of spacetime itself, from the behavior of known fields in extreme conditions, from the quantum geometry of gravity. They do not need speculative extra fields. They do not need carefully tuned initial conditions imposed from outside. The physics emerges naturally, from the ground up, as a consequence of the fundamental structure of the theory. This is not the same as saying the problem is solved. It is far from solved. But the direction of travel is encouraging. The theories are becoming more constrained, more predictive, more honestly confronted with data. The gap between the mathematical frameworks of quantum gravity and the observable universe is narrowing. And the criterion by which these theories are ultimately judged is not philosophical elegance, not mathematical beauty, not conceptual simplicity, though all of these matter in the development of good theories. The final criterion is the one that has always defined science at its best. Do the predictions match what we actually observe? That question, simple in statement, profound in implication, is the thread that runs through all of this work. From the faintest temperature fluctuations in the microwave sky, to the spectral content of gravitational wave backgrounds, to the statistical distribution of galaxies across the observable universe, the cosmos is speaking. Slowly, in a language that requires centuries of effort to learn. We are still learning it. And the most important sentences have not yet been read.